All right, we're going to do section 9.1, page 445, number 32, which reads, determine the convergence or divergence of the sequence with given nth term. If the sequence converges, find its limit. So in this case, an is equal to 2n over n plus 3. Now, if we want to determine if the sequence converges or diverges, that means we really want to know what the limit is. And if the limit is equal to a number, 14, 107, then we can say that that sequence converges. If the limit is going to be undefined or the limit is equal to infinity, then the sequence diverges. So really determining convergence or divergence is the same thing as solving the limit. So we're going to want to figure out the limit as n goes to infinity of our general term here, which is 2n over n plus 3. And in your journal, you were supposed to refresh your memory about limits. And when we come across a limit, as we did earlier in this book, we had a bunch of steps that we tried to apply when we were trying to evaluate a limit. And I hope that you wrote those down and you remembered what they were. The first thing to try to do when solving a limit is to substitute in, which means you take the value down here that n goes to, and you substitute in that infinity everywhere you see an n. Well, if we do that, if we substitute in, we're going to end up with 2 infinity over infinity plus 3, and that really isn't going to be much help. So the second thing that we were supposed to try when we were evaluating limits was to see if we could simplify or do some algebra. Was there a higher order polynomial that we could factor? Was there something that we could cancel? And in this case, this expression is pretty simple, and there isn't really any cancellation that we could do. Well, the third thing on our list to try when we're evaluating limits is to look at the end behavior. And pretty much when we looked at the end behavior model, we assumed that any polynomial really acted like its highest order term. Now 2n really is a polynomial. It's an first order polynomial, and so it's going to behave as 2n. But in the denominator, we've got n plus 3. Well, that's a polynomial as well, and we can assume using end behavior modeling that n plus 3 is really going to behave as n goes to infinity, which kind of makes sense. As n gets to be very, 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 very large, whether or not we add 3 to it isn't really going to matter very much. So let's try to use that approach. So that means I can rewrite my limit, the limit as n goes to infinity, is now going to be 2n. Can't really do anything about the numerator, but the denominator I'm going to rewrite as n because we're going to assume that n plus 3 will behave as n. Well, now I go back and I go through my list again. Can I substitute in? Still not really going to help. But now I can simplify. I've got an n in the numerator and an n in the denominator, and I can cross those out, and this is going to give me then the limit as n goes to infinity of 2, which is just going to be equal to 2. Now, because this limit is equal to an actual number, I know that my sequence converges, and I know that it's going to converge to 2. And that is the answer to my question.